In this short lecture, we're going to talk about Euler's equation. Let's first come up with a differential equation that we might want to solve. I know it sounds a little bit ridiculous, but let's say we have a spring attached to a damper which has a panel attached to it with no mass. We displace it and say we give it an initial velocity. So we'll displace it x and we'll give it an initial velocity and we'll let it loose. Now we know what's going to happen is it's going to go back to its undamped state, and the differential equation that you would if you had a mass would be mx double dot plus c x dot plus kx equals 0. However, we have none of that. So we only have this differential equation. For that matter, I can change to this and go ahead and change to this. So if you look at it, it's a fairly simple differential equation. Now let's start taking a look at how Euler method comes about, and we will expose through our homework assignment some of the weaknesses in it, but it's a good first step. Now if we ignore this and start thinking about just a Taylor series expansion, we start with this some function what we are beginning to do, alright, is say we have some function f as a function of time, or maybe I better yet just go ahead and say it's x as a function of time. And we pick some particular time location, say A, and we want to expand about that. So we might want to say, I want to know what x at a particular time is, where say that time might be here or might be anywhere on there. So what we do is we come up x at time A plus x dot times, let's see, maybe I need to put the times in front of it, evaluated at A plus x double dot over 2, but essentially it's a factorial, and 2 factorial is 2, and we will move this over, and I may move it back here shortly, but the reason I'm moving it over is to put this right here. Should have moved it there earlier. Plus t minus a to the third power x 3 time derivatives over 3 factorial, and the series goes on and on and on. Now, in other words, it goes to 4 derivatives, and then 5, and then 6, and it goes to infinity actually. So I guess technically I should go ahead and but I don't, well, we'll just stop with that and say we're going to truncate it. So I'll just say it goes on. This is the n. This, you notice here, I'll mention it this way. This matches that, matches the number of time derivatives. and you just keep it going to 4, 5, 6, all the way out to infinity. So this tells you that given the functional value at a, the functional derivative there, the second derivative, the third derivative, and so on, I can actually determine the x at any point in time if I have the value at a and all of its derivatives. Now what happens often is we go in and truncate the series. If you go in and truncate it here, you can move this to the other side and divide this underneath, and you can pretty much say that x at some value of a is equal to t minus a over t minus a. Now, how are we going to make use of this? And what are we going to do? Well, actually, we're going to solve this differential equation using this, but we're going to do it in a way that matches the calling sequence of ODE in MATLAB. The reason we're going to do it this way is that we'll get acclimated to actually what's going on inside MATLAB while at the same time going ahead and solving this. So let's go in and take a look at the MATLAB ODE and see the calling sequences and see what it wants. Then what we're going to do is we're going to build a function that looks like ODE so that you understand what's happening in ODE, but we're only going to do it using Euler. It'll come together as time goes by here. Now let's look at the ODE 4.5 and what actually may take place inside ODE 4.5. What you see is here's the calling sequence. You have something sitting here, but you have something called solver. What you'll notice is that there's an ODE 2.3, a 4.5, a 1.1.3, all the way out through here. There's a large number, but they've unified the calling sequence, which is a good idea. In essence, we just need to pay attention to this sequence. And let's pay attention here and look at each one of these. This one is ODE function. It says a function that evaluates the right side of the differential equations. Well, let's take a look at this and see. Okay, it values the right side of the differential equation. Now, what was that in our case? In our case, that's going to be this. This is the right side of our differential equation. So we're going to keep that in mind. We're going to solve a first-order differential equation, which the solution will have an exponential on it. And we're going to pay close attention to how this occurs. So what he wants in here, he wants a function that looks like that. So we're going to look down in the page here a little bit and look at the calling sequence and what that function should look like. And then we're going to build Euler about it, and we're going to solve our differential equation. Let's look down at the calling sequence, and let's go ahead and build the calling sequence. If you look down, as far down as you can, and then find yourself so these are all second orders. I'm looking for a first order, which I'm not seeing right off, but I am seeing it right here. Now it's a system, though. Well, in any case, here's our function. We're going to go ahead and copy this. And we went ahead and pasted it right here. But this is not really what I'm interested in. we're only going to have one time coming at us and one value. In this particular case, we're going to call it x. So essentially we need to find dx, and I'm going to call it dx dt. If we look back at our equation, dx dt is just simply minus k over cx. Dx dt is equal to minus c over k times x. And that's it. Now what I'm going to do, see if I can delete all the rest of this out. And I'm going to call it, instead of that, I'm going to call it something like first order DFQ. Some people do not, but I like to put it in there to basically encapsulate the call. Now at this particular point, we don't know C or we don't know K. I'm just going to come up with some values. C is equal to 10 and K is equal to 12, just random choices. I can come back and change that later, but that's essentially it. Now how am I going to solve this? Well, let's do it by hand first. And you know what? Instead of doing that, to simplify, I'm going to say C over K. C over K, that'll just give me a time constant. I'll say 5. Now let's go ahead and save it. It wants to see it with the same name. We're going to save it in the directory so we can access it. We're going to go back, and now we're going to solve this thing by hand. Let's say, this is the first order differential equation we're looking at. And let's say the initial position, or the initial position here is 10. We can make it anything we want, but so let's just carry it as x naught for the moment, and then we'll start inserting it. So it's a first order differential equation, so I spoke sort of out of turn earlier because I talked about an initial velocity. But let's say we pull the thing out and let it loose. That was an incorrect statement because we had no mass, so we only need the initial position here. So now let's build ourselves a little table. We'll say our little table has, first I'll make our table have time. Then what we'll do is we'll have our table say x. So this is pretty simple right here, the first row of this table. This will be x naught, and I'm going to just pick it as 5. The next thing I need to know is I need to know x dot. Now where am I going to get that? Except that that's the case. Oops, trying to get it to move down. So let's look back and see, what did I decide C over K was? I decided it was going to be 5. Let's change it to something, because I have too many 5s here. Let's change it to 2. So I decided that this is going to be x dot is equal to minus 2x. So I could pretty much say that if that's the case, then this thing should be minus 10 at time is equal to 0. So your key here is you're reading across the column. Now what do you need to know next? Well, I need to know the next value would be eventually, I need to know x. Now, how am I going to get this? Well, let me go all the way back, make this space available, and then I'm going to basically go in and take a look at this. If in fact someone were to give me a value of x at time A, let's just take our first instant. Time A this time will be 0. Then I'm going to go in and I'm going to say t minus a x naught at A. So what I'm saying here is, x dot at A. This value, if we say A is equal to 0, we may want to find out what the derivative is here, which would be that minus 10, multiplied times a time step, which is the value you're looking at, and finding out the value at t being x naught plus, say, a delta time times the valuation at A. So what we have to establish is that we're looking at a certain delta t. Let's go ahead and take 0.1. So now the equation becomes, in a standard form of the equation, would become x at some t is equal to some x at t minus delta t, the time step before, plus delta t times the evaluation at t minus delta t. So what I'm saying here is I take this column now, I'll multiply it times delta t times x dot. Turns out that my delta t is always going to be 0.1, so I get 0.1 times 10 or minus 1. Then what I do is I take the x, or I'm sorry, I should do it like this. I should take this value, which would be right here, 5, plus this value, which would be minus 1. It'd give me 4, and this will be x at t plus delta t. So the other way to write this is I could take this, and this would be the equivalent. So then I take this, put it over at 4, multiply 2 times that, gives me 8. Multiply that, 0.8. Take the 4 minus 0.8, gives me here. I'm going to take a pause and I'm going to draw up something else. Most everybody is somewhat familiar with Excel, so I'm going to go into it and solve this equation. And we'll plot it as well. So we'll start with our initial and go 0.1, and then we'll just drag it down to about that value. I'll start with my initial position. I might want to insert a column here. I'm not sure that I actually do. I'm going to go ahead and say this one is equal to minus 2 times the value in the previous column, which would be this one, and then this one would be equal to 0.1 times the value in the previous column. And then finally, let's see if I can get this out of the way. So this is this column, and this is the last column. The last column is equal to the exit the last time step plus this value. Now the thing I'm going to have to do here is I'm going to have to say this value is equal to the value previously to it. Copy this down one step, and then I take this row, copy it continually down. Now if I want to plot it, I could plot these two columns, and let's see, data, no, insert, and let's just do it like that. So what you get is a solution that looks like this. This is something we'd expect. You pull it out, let it loose, it basically comes back to a 0. Okay, so we did this in Excel real quick. Now, how do we do this in MATLAB? And it's not that bad. Let's solve this differential equation then. Okay, now what I want to do is I want to make sure that I'm calling it with the sequence that you would use to do ODE45. So I want it to look like this. So I'm going to call just like this. I'm going to copy this. I'm going to do a copy. And now I'm going to go over and create something new here. And I'll just call it, it doesn't matter what I call it here. I'll just do it this way. Function Euler test, or here's what I'll do. Do a V Euler. I'll call my ODE function. Since I'm going to exactly mimic the MATLAB calling sequence, I'm going to have to use what's called a functional evaluation. Let's take a look at this real quick. Essentially, this indicates a function to be called. You have a function handle, and you notice when you send it into this routine, which is right down here, he essentially calls or evaluates that function with those arguments. So essentially what I'm going to do is I'm going to go ahead and copy this. I'm going to drop it over in here, put a few hits to this, and I'm going to do a paste, paste, paste. I'm going to have to fix that a little bit. Now I think what we're going to do is we're going to be calling this at times and then positions. So I'll do it like that for the moment. And really the only thing coming out is dx dt, but the handle is going to be that. Now the question is what are these other values for? In this particular case, I'm going to just target a first order differential equation. T-span is going to be a span of time that we'll have to put in. So what I'll do is T-span. We will step our way through this. And make sure. Here, I'll even do it this way. I'll step it even a little bit better. Okay, n is equal to length. This way we can, instead of doing it the way I would normally do it, I'm going to do it so that I can break point. We can look at everything that's going on. So what I will do, I will say dt or I will say I is equal to 1 to n, which is the length of this. Then I'll say dt is equal to t span of I. And then what I'm going to do, hang on, I'm going to call this evaluated function here. I am going to go ahead and keep it from, or I'm going to suppress the output. Then I'm going to go back and I'm going to say if I'm at a certain time at this point, if I have this derivative, and I'm going to assume that all of these, the distance between any two member of t-span is the same, so therefore dt is equal to t-span 2 minus t-span 1. And then I'm going to say x sub I is equal to, now what I need to do, I need to fix something here before I do that. X sub 1 would equal to, I'll call it x naught, and I'll change this to x naught. It's the initial condition. Then I'm going to start in on the next time step. It's going to be equal to x sub I minus 1 times dt times dx dt. I'm going to go ahead and take that off. I don't like looking at that. And essentially I'll end, and then before I send it back I'll say t is equal to t. I probably should go ahead and change these two variables, x, and leave that as t. I'll go ahead and put this in, well, I'll go ahead and make it a smaller x. I don't think I have a t in here, so I'll make it a smaller t. And then what I will do is I'm basically trying to make it very readable. Now I think I may have messed up one particular point, but I'm going to fix it here in a second. T at I is equal to t at I minus 1 plus dt. Okay, now I need to send in the current time I'm at right here. The current time is not, actually it doesn't get calculated anyway, but okay, so then I need to send in the time, or the x value at the last location. Wait, I need to fix this. This is not correct. There. Now, I believe that, let's go ahead and put another n there. I believe that'll get us. So let's try to call this in another routine. What we're going to do is I'm going to just say x naught is equal to 5. T span is equal to, say, 0.1 to, say, 15. Then I'm going to call my Euler. Looks like this. But my ODE function is called this, first order differential equation. There's my t-span, there's my x naught. And we'll just call it Euler testing. Then I'll try to do a plot of time and position. So let's run this. Now I'm going to hit F11, takes me into here, and I'm going to step through this. Okay, there's my T-span, there's my X0, there's my OD function. So I think at this point I have the initial, I have the time. I think somehow something happened here. This was the DT. Okay, that is an error. Take that out, go back, run it again. As a matter of fact, let's just go in here and put a breakpoint right here. And hit this thing, hit it again. Okay. Now, I'll hit F11, and you notice I ended up in this routine with t is equal to 0 and x is equal to 5. I get my minus 10, which was the same thing that was in, hang on, let's see if I can find it. It was the same thing that was sitting right here. Hit it F11 again, and I end up coming out of here. I end up with that, minus 10, the 0.1. This one, there's your I, 2, so it's looking for, if I highlight it and push the, no, I can't do it that way. Okay, I'm stepped it one more time. Okay, I end up with that. Okay, let's evaluate the selection. Let's make sure we've got this right. Okay, DT 0.1 DXT minus 10. So I want to evaluate this one. I right click and do evaluate selection. I got minus 1. I minus 1. Wait, that should be 5. Oh, that's not a times. Sorry. That is a plus. Let me go back and fix that. All right, we'll eventually get this thing set. F11, go through here with the F10. We're just looping through here. There we go, getting it better. So at this particular point, I could do a step out, hit F10, look at my plot, looks pretty much like that. Compare it to this one. I think what I'd like to do is now shorten it down. I went too far here. So let's see if we can figure out whether or not this is the correct value, or these two match. First of all, I notice that somewhere along the way I get a point that is 0.7 and 1.48. So let me look at this value. The times are there and the x's are there. How do we get them together? I could do that, or I could do this with an x, and I can get them that way. So if you see a 0.7 and you see a 1.486, then you're satisfied, moderately so, because 0.7 and 1.485 are 86. So MATLAB and Excel came up with the same answer here. So in essence, if we wanted to change this, we could make one simple change. Now we see how, how this thing is built. Here's an Euler solution to it. we can make one simple change and solve it with ODE. Tell you how we'll do it. We'll do a copy, and then we will do a paste, and we'll change the Euler to ODE 45. But this time we're going to call this X1, say. So an X1, and I'm going to compare the two of them. I'll make one blue, and I'll make the other one red. Save it. The first one would be ODE 45. The second one would be Euler. I'll put a breakpoint right there just so I can save it. If you look at the plot, you'll see something really interesting. There are the two solutions. Let's go ahead and instead of doing it up to 15, let's quit it, run it again, look at the plot, and you start seeing differences here. Now, I'll go ahead and do the one step so I can see which one's which, and we'll look at these two, and you realize Euler is the red, and ODE 45 is the blue. If I got the thing correct, yeah, I got the blue sequence for ODE 45 here. Yeah. So why are they different? Well, let's experiment one more time. Run it and take a look at it. What we find out is, ooh, they're not that much different. If you decrease your time step, you can get them to be the same answer. Okay, in the next video, I'm going to stop here, but in the next video we're going to talk about how can we do a vectored form of Euler and ODE. We're going to stick to Euler just so we comprehend what's going on and how this is being calculated. And we will transition to ODE 45 later.